Okay, well, thank you everyone for coming today. Today we have a fascinating talk by John Cassano about interactions between the polar atmosphere and the cryosphere from observations and modeling. As I think most of you know, maybe not all of you know, is that John is our new-ish lead scientist at NSIDC. He's in ATOP, that's the Department of Atmosphere and Oceans, and he's a fellow of series like I am. And as I mentioned, lead scientist at NSIDC. And he's been doing polar research for a long, long time, both Arctic and Antarctic, but with a special fascination, I think, in the Antarctic. So with that, John, please take it away.
Great. Thanks, Mark. Yeah, so like Mark said, I've been at NSIDC since the fall of last year, and I've been getting to meet a lot of you virtually and learn about the things that you're doing. And my thought with the seminar today was to give you a sense of what I do for research as well as my research group. So, a lot of what I'm going to show here today are bits from work that other members of my group have done. But the theme mostly is going to be looking at how the atmosphere interacts with the underlying surface in the polar regions, whether it's in the Antarctic or the Arctic. And so I got a lot of different topics I'm going to talk about, all pretty high level, not in too much depth. We'll spend most of the time talking about the things that you see listed on the left side. So we'll talk about work we've done looking at the Antarctic boundary layer with automatic weather stations, radiosondes, and unmanned aircraft. And then we'll pivot up to the Arctic and look at some work I was involved with this in 2020 using unmanned aircraft as part of Mosaic to look at the boundary layer over Arctic sea ice. And then at the end of the talk, I'll pivot again and talk more about larger scale atmospheric processes, sort of synoptic scale weather systems. And we'll talk about Arctic cyclones and synoptic climatology. We'll talk a little bit about modeling work that my group does and decadal prediction, and then a sort of a new area for us, talk about using some weather radar data to look at the Antarctic atmosphere. So my group, our research focus primarily is, like I said, on the interactions that occur between the atmosphere and other parts of the polar climate system. And we do this by taking part in observational field campaigns where we make observations in the lower part of the atmosphere and see how that bottom part of the atmosphere is responding to whatever the underlying surface is, whether it's sea ice or ice sheets or whatever it may be. And I've been involved in 14 Antarctic field campaigns starting when I was a graduate student. And then I've done three-ish Arctic campaigns. The most recent was last year, part of the Mosaic project. We also analyze existing data sets. So atmospheric reanalyses are ones that we use a lot, similar to Mark and his group, and also model data sets. So things like the CMIP Climate Model Archive or Polar Cortex data sets. And we do this mostly studying synoptic scale weather systems, their role in polar climate, and interactions with lower latitudes. And then finally, we also develop and apply regional weather and climate models to study the polar atmosphere and its interactions with other parts of the polar climate system. So we'll see little bits and pieces of all of this today. And when I give a talk like this, where we're talking about this bottom part of the atmosphere, I like to just spend a little bit of time to get everyone up to speed with this part of the atmosphere. And so this bottom part of the atmosphere is called the atmospheric boundary layer. And the depth of this boundary layer can vary from only a few meters under very stable conditions like you might find over the Antarctic ice sheet in the winter to a kilometer or more under conditions of strong surface heating. So in Denver in the summer, the boundary layer might be 5 or 6 kilometers deep. But the boundary layer, what's important about it is that it's the part of the atmosphere that's directly interacting with the underlying surface. It's also a turbulent part of the atmosphere. That's what characterizes the boundary layer, is its turbulence. And it's that turbulence that acts to transport properties between the surface and the atmosphere. So whether that's heat or moisture or momentum or trace gases or whatever it may be, but that exchange is really taking place in the boundary layer. And so our interest is in understanding how the boundary layer behaves and how it modulates those interactions with the underlying surface. So I've already said why we care about it scientifically. That's the last bullet point on this slide. But all of us actually probably should care about the boundary layer because it's where we live. And I like to remind people that your perception of the atmosphere is very much shaped by the fact that you live in the boundary layer. So the fact that, a normal aspect of weather in all of our minds is that it's cold in the morning, it's warm in the afternoon. That's purely a boundary layer feature. If you lived above the boundary layer, you wouldn't see that at all. The temperature would vary on multi-day timescales. Another aspect of weather that we experience all the time when we step outside is that the wind blows and it's gusty, but those gusts of wind are turbulence. And if you were above the boundary layer, there's no turbulence. The atmosphere is laminar and you wouldn't feel any gustiness of the wind. A flag that's placed above the boundary layer wouldn't flap. So things that you take for granted about the behavior of weather and the atmosphere are really shaped by the fact that we live within the boundary layer. So I just like to remind people of that. So, when you walk outside after the seminar today and, you feel the winds gusting, you can think about that it's really a special part of the atmosphere that we're in that isn't typical of the vast depth of the atmosphere. So how we study the boundary layer varies depending on, the conditions that we're trying to sample and the environment that we're working in. Most of our work is in the polar regions. A lot of it has been in the Antarctic. The Antarctic is a very short summer field season. And so most of the data that we get in the Antarctic to look at the atmosphere or any part of the Antarctic system comes from autonomous observing systems. And I've been involved from when I was a master's student at the University of Wisconsin with a project that deployed automatic weather stations around the Antarctic continent. About 10 years ago now, we worked with the group at the University of Wisconsin to install a tall automatic weather station. So most of the weather stations are 3 meters tall. They measure conditions right near the surface and that's it. And about 10 years ago, we had a project where we installed a 30-meter tower that we called the Tall Tower AWS. And this tall tower was installed on the Ross Ice Shelf. So this is basically flat, floating ice sheet about the size of France. So it's a nice place to do boundary layer work. It's a very homogeneous environment. And this tower measures temperature and humidity, wind speed and direction and pressure continuously. It reports data every 1 minute. And we make these measurements at multiple levels on this tower. And you can see in this picture, there are little arrow veins at a bunch of different heights. And there are also temperature and humidity measurements being made at those locations. So we took data from this tower and we wanted to look at how the temperature over that 30-meter depth of the atmosphere varied across this multi-year data set that we were collecting with the tower. So the data we used was 10-minute observations, and we had even higher time resolution than that, but we used 10-minute observations and we looked at a 2-year period. So we had more than 100,000 observations of temperature and wind profiles over this 30-meter depth of atmosphere over the Ross Ice Shelf. And that's a lot of data to try and make sense of. And one of the tools that we use for a lot of the work, and it shows up in some other things that I'll talk about later, is a neural network pattern identification algorithm called self-organizing maps, or SOMs. And so what we did is we took these 100,000 temperature profiles from this tower and put them into this neural network algorithm and asked it to give us a representation of the different types of temperature profiles that we see. And that's what you're looking at here. So each one of these little postage stamps is showing you the temperature profile, and it's a temperature anomaly ranging from -6 to +6 and over the depth of the tower from 0 to 30 meters. And this algorithm organizes the patterns such that similar patterns are shown close to each other in this graphic representation. And so what you see is the patterns on the right side, the temperature is basically constant with height, the atmosphere is well mixed. And then as you move from right to left, you see that the temperature increases with height. This is a stable stratification. And so we can see the range of temperature profiles that are present in this multi-year data set. And we see it in a very compact way. And the shape of this temperature profile really dictates things like the intensity of turbulence that's present. It helps us understand how the atmosphere is interacting with the underlying surface. So this was work I did with a former graduate student of mine, Melissa Nigro, and we published a couple of papers that I've listed on the bottom here. The one example of how we use this that I want to show here involves evaluating weather forecasting model. So the left picture is showing how often each of these 30 different patterns that I showed you on the previous slide, how often each one of those patterns occurs over the 2-year data set. And the darker the shading, the more frequent the pattern occurs. And what you see is that those patterns on the right side, the well-mixed patterns, occurred the majority of the time. And that as we moved from right to left across our self-organizing map, the patterns became less frequent. So these very stable patterns generally were not occurring very often. And this was a bit of a surprise to us when we analyzed the data, because one of the things that you read in textbooks when you look at polar regions is the presence of these strong temperature inversions is a defining characteristic of the atmosphere in the polar regions. And it turns out that at this site, that's not the case, that a lot of times the atmosphere is actually well mixed, and it has to do with the fact that this site gets very strong winds that generate turbulence and mix the atmosphere. So these are the observations. And then on the right, what we did is we took the same 2 years of weather forecast from an operational forecast model that's used in the Antarctic called the Antarctic Mesoscale Prediction System, or AMPS. And we calculated how often it simulated these different temperature profiles over the lowest 30 meters of the atmosphere. And what you see is that the gray shading on the right is very different than on the left. That AMPS tends to simulate a lot of these sort of moderate stability patterns in the bottom center of the SOM most frequently, and doesn't really simulate near as many of the well-mixed conditions on the far right. The other thing I'll point out is that AMPS also fails to simulate the very strongest stability patterns. It's a factor of 10 less frequent in the model than in the observations. And so this lets us really understand what the model is doing versus what's happening in the observations. And of course, as modelers, as model developers, we want to not only look at, is the model reproducing what's observed, but try to understand why it's failing. And so this next slide, which I won't go into a lot of detail, but here we're basically saying, we're looking at the observations and saying, when the observations are observing a certain pattern, one of these 30 different boxes, what is the model simulating at the same time? And on the left, it's the colors are showing us how strong the temperature change is over the depth of the tower. And red means that the model is simulating a stronger temperature change over the depth of the 30 meters, and blue means the model is simulating a temperature change that's weaker than observed. And so what you see is that these very stable patterns where the temperature increased a lot, the model is underestimating how much the temperature increases. And these patterns where the temperature was relatively constant with height, the model is simulating that the temperature actually is changing more in the vertical direction than was observed. And then the picture on the bottom right is doing the same thing, but looking at the observed versus modeled wind speed for each of these patterns. And red means that the model is simulating winds that are too strong, and blue means that it's simulating winds that are too weak. And we can put these two things together and sort of start to diagnose why the model is failing. Why is it getting the wrong vertical temperature gradient? And a lot of it has to do with the fact that the model simulates overly strong winds, and those strong winds tend to mix out the really stable patterns on the left side of the SOM. So it gave us a very powerful way to look at a very large data set, look at it on timescales where the atmosphere is operating, the boundary layer operates on minute or shorter timescales. And so we're evaluating the model on these very short timescales and really getting into understanding the processes that are shaping why the model does or doesn't do well. And so this has been a really powerful way for us to analyze data. And I'll show you some other examples of self-organizing maps a little bit later. A more current project that we're working on is doing something very similar, but this is using weather balloon radiosonde observations of the Antarctic boundary layer. And this is data that was collected as part of a DOE project called the ARM West Antarctic Radiation Experiment, or AWARE. This is work that one of my graduate students, Mackenzie Dice, is working on. And the analysis that I'll show here is preparatory for Mackenzie and I to be going down to Antarctica to install a new 30-meter tower in West Antarctica, which is the warmest or the most rapidly warming part of the ice sheet in Antarctica, as well as to do a multi-week field campaign using unmanned aircraft to make measurements in the boundary layer. Mackenzie and I are supposed to be in Antarctica right now. We were supposed to be down for all of January of this year, but COVID has pushed us back at least a year. And so Mackenzie took these weather balloon launches, which happen twice a day, and she realized 1 year that this AWARE campaign was taking place. And she used self-organizing maps in a similar way to what I just showed to look at these vertical temperature profiles in this year-long data set. And so here is Tom that Mackenzie trained. Now, again, we're looking at temperature anomalies going from 0 to 15 degrees, and the depth range now is from 0 to 300 meters. So this is encompassing not just the bottom part of the boundary layer, but really capturing the majority of the depth of the atmospheric boundary layer. And then the self-organizing map that Mackenzie has created is, again, organized in a similar way. So in this case, the strongest stability patterns are on the right side, and as I move to the left, the temperature change in the vertical direction gets less and less. The atmosphere becomes less stable. And one of the reasons that I put this up is not only to highlight the work that Mackenzie is doing, but also to show one of the ways that we're visualizing this data. So the black line is what the algorithm gives us and says this is a representative pattern. But then the thin green lines are all of the observations that correspond to that pattern. So the algorithm tells you which pattern each observation that you've used corresponds to. And you can see, how this algorithm really is very effectively distinguishing the range of conditions that are present in this data set. That, we can take these nearly 300 radiosonde observations and represent them with 20 different patterns and capture pretty much all of the variability that's present. So this is a real powerful way for us to analyze these types of data sets. And then a couple of just results from Mackenzie's work. So the top left is just showing how frequently each of those different temperature profile patterns occurs. And again, what we see is the least stable, the ones with the smallest temperature change, which is the bottom left in this case, occur most frequently. And the strongest stability patterns tend to occur less frequently. And then another thing that we can do with this type of analysis is take other observations that were made at the same time and see what conditions are present for each of these different types of temperature profile patterns. And that's what we've done on the bottom right. And here we're looking at downwelling long wave radiation. So this is the radiation being emitted by the atmosphere, and that is a large driver of the surface energy budget, which then shapes what the boundary layer looks like and the temperature profile. And here the dark shading indicates larger values, and these are in watts per meter squared. And you can see those well-mixed patterns tend to be associated with the most downwelling long wave radiation. And as you move diagonally from bottom left to top right, you tend to move to less and less downwelling long wave radiation. And that exactly matches what we expect, that these inversion conditions in the top right occur when the atmosphere is clear. There are no clouds, lots of radiation is escaping to space, and not much is coming back down. And it strongly cools the surface and creates these inversion conditions. And so we can really start to understand what are the processes that drive the occurrence of these different patterns. And so that's the work that Mackenzie is doing. Now, another part of the work that my group has been involved with to study the boundary layer in the polar regions is using unmanned aircraft. And the first campaign that we did was back in 2009. We used sort of a moderate-sized unmanned aircraft called an aerosonde, and I'll show you a picture of one in a minute, to make measurements in a place in Antarctica called Terra Nova Bay. And Terra Nova Bay was where we wanted to go because there are a few features here that make it particularly interesting from a climate perspective. So first, Terra Nova Bay is an area that has a recurring wintertime polynya. And so polynya is just an area of open water surrounded by sea ice or land. And in the winter in Antarctica, you'd expect that all of the sea ice surrounding, or all the ocean surrounding the continent would be covered in sea ice. But there are a few places where these polynyas happen, where you have open water. And that presence of open water means that the relatively warm water is able to lose a lot of heat and moisture up into the atmosphere, and the atmosphere is able to deposit its momentum into the ocean. And so this is a very critical environment for exchange between the polar ocean and the polar atmosphere. The reason this polynya exists in Terra Nova Bay is that there are very strong katabatic winds that occur here. Katabatic winds are just cold, dense air that drains off of elevated terrain, the East Antarctic Plateau in this case. And that air, because it's so cold and dense, accelerates downslope just like water flows downhill. And it gets funneled into certain places near the coast of the continent. And Terra Nova Bay happens to be one of them. The wind speeds in Terra Nova Bay in the winter average about 20 meters per second, or about 45 miles an hour. But there have been months of observations at Terra Nova Bay where the wind speed is averaged stronger than hurricane force for the entire month. So it's an exceptional place in terms of the strength of the winds. And it's those strong winds that are blowing off the continent that push the sea ice away from the coast and cause the polynya to be present. And then the interaction of those strong winds with the open water that's present in the polynya generates a lot of turbulence that allows for a very large heat loss from the ocean into the atmosphere. That, of course, modifies the atmosphere, but it also modifies the ocean and creates very cold, very saline water that feeds into what's called Antarctic bottom water. And Antarctic bottom water is the densest water in the world ocean, and it helps drive the thermohaline circulation in the oceans. And so we could go to this, small sort of 50 by 50 kilometer portion of the Antarctic coast and make measurements, but be looking at things that have global climatic significance in terms of, ocean circulation and things like that. And so the work that we did in Terra Nova Bay, we went there twice with the unmanned aircraft, these aerosondes, in 2009 and 2012. And these two campaigns were the first time that anyone had ever made in situ wintertime observations of the atmosphere over Terra Nova Bay. So there are moorings that made measurements within the ocean, but we didn't have any data over the polynya itself in the atmosphere. And so that's what we did. And then I'll also point out that these flights that my group led in 2009, along with flights that the British Antarctic Survey did that same winter, were the first time that there were any unmanned aircraft flights done in the Antarctic for research. So we were really on the leading edge of that. So I want to show you a little bit from this project as well. So this is the aerosonde. It's a relatively modest-sized drone. So the wingspan's about 3.6 meters. It weighs about 20 kilograms. It gets launched off the top of a pickup truck. So the pickup truck accelerates up to about 50 miles an hour. Once the truck gets up to that speed, the drone lifts off and then flies off on its own. I'll show you a video of what that launch looks like because they're kind of impressive to see. And then, like I said, we had two campaigns in 2009 and 2012. We did a total of 30 flights and about 300 flight hours with the aircraft. And then there are some specifications about the aircraft. The couple of ones that I want to point out, aside from the size, which I just mentioned, is the endurance. So we could do flights up to about 19 hours, and we did flights up to about that limit while we were down there. That meant we could fly more than 1,000 kilometers, which was useful because Terra Nova Bay was about 300 kilometers away from where we were doing our launches, which was near Mcmurdo Station. And the primary observations were temperature, humidity, wind, and pressure, so atmospheric state. And then I'll show you what one of these launches look like. So this is in September 2012. We're out on the ice runway that is sort of the main runway that the U.S. Antarctic program uses. In September, there aren't any intercontinental flights or any flights that are taking place in Antarctica. So scientists can come down to Antarctica middle or end of August, and that's when we went down. And I did this work with Mark Seefelt was with me, one of the research scientists in my group. So we went to Antarctica in August when there were a couple of flights that flew from New Zealand down to Mcmurdo Station. And then there are no flights again until the beginning of October. And that's what made going down to do drone flights at this time of year appealing, because we had the free range of, thousands and thousands of kilometers of airspace. We knew that there was no one else going to be in the airspace. But anyway, the drone, the Aerosonde, gets launched off this pickup truck, and we use the runway as a place where we could drive our pickup truck up to about 50 miles an hour. And so what you're going to see is the pickup truck is right here with the headlights on. It's going to be racing towards us. The Aerosonde is sitting on top of it. And you'll see once the pickup truck gets up to speed, the Aerosonde lifts off and flies off into the sunset to do its 15-hour mission sampling up at Terra Nova Bay. And so, we did, like I said, about 30 times over the 2 field seasons that we were down. And then just to show you a little bit of the data that we collected. So I'm going to show you a sequence of slides. The bottom left is a visible satellite image of Terra Nova Bay, and then the top right is a map view showing wind observations from the Aerosonde. But just to orient you, the scale here is maybe about 50 or 60 kilometers across. The Antarctic coastline runs almost straight up the middle of this image. So mostly everything to the right is sea ice. Everything to the left is land. There are mountains here. There are glacial valleys. Here's a bit of floating glacier tongue, the Dragowski ice tongue. And then right at the coast, you can see some dark areas in the satellite image. This is areas of open water. So the winds are blowing off the continent, these very strong katabatic winds, and they're starting to push the sea ice away from the coast. This is the beginnings of the Plenia. And then the top right image is showing the winds that are measured by the Aerosonde. This is at 100-meter height. The wind speeds are shown by this color bar. These are in meters per second. So on this flight, the strongest winds are about 30 meters per second, or about 65 miles an hour. The next day, we flew back up again, a second mission. The wind speeds had increased to approaching about 40 meters per second. And you can see it's a very narrow jet of wind that's draining from these glacial valleys on the Antarctic continent, that the wind speeds, over, tens of kilometers drop from basically calm to, close to hurricane force winds. And so it's a very exceptional environment. And what you can see is these winds have increased from the previous day. The sea ice is beginning to be pushed further away. The Plenia is opening up. A few days later, the winds are still blowing, about 35 or 40 meters per second. And now we have a fully developed Plenia that's open. So lots of open water. All the light that you see in this Plenia area that extends out to the edge of the tip of the Dragowski ice tongue is new sea ice that's forming as heat is extracted from the ocean by this very turbulent flow. And then this, the bottom 2 little pictures are a couple of days later. The katabatic winds are dying down. The Plenia is still wide open though. But the main picture here is showing observations from the Aerosonde as it flew from near the coast on the left side of the image, about 40 kilometers downwind from the coast on the right side of the image. And what I'm showing is temperature. These are the blue dots, dew point temperature, which is a measure of humidity, and then wind speed in the black dots. And what you can see is, or what we were trying to measure, is how the atmosphere is being modified as it passes over this area of open water in the Plenia. And so what you see is that the temperature warms up, something of the order of about 4 degrees Celsius. The dew point temperature warms, about 10 degrees Celsius. So you can see from these observations the heat and moisture that's being put into the atmosphere as it passes over this area of open water. And then the wind speed drops by about 5 or 7 meters per second over this distance, from about 20 meters per second to something like 13 or 14 meters per second. And this is reflecting that momentum transfer from the atmosphere into the ocean. So these very strong winds deposit their momentum into the ocean. They generate huge waves, they generate mixing in the ocean, and all of those things. And so this one image really encapsulates a lot of what we were trying to do, to understand the exchange between the ocean and the atmosphere in this Terra Nova Bay Plenia environment. And then one last picture that I'll show from this campaign. So these are temperature profiles that we acquired over the Plenia at different distances from the coast with the Aerosonde. So blue is right at the coast, and then about every 10 kilometers, we have the green, the orange, and the red. And what you see is this warming that's confined to the lowest, about 400 meters of the atmosphere. And you can see above that, the atmosphere is not feeling anything from the Plenia. But from these profiles, we can calculate exactly how much heat is being added to the atmosphere and calculate what that energy exchange is from the ocean to the atmosphere. And in this case, the biggest energy exchange between the green and orange profile is about 600 watts per meter squared. So that's the amount of energy the ocean is losing as a result of the presence of this plenia. And we could do the same thing for moisture, and we can do the same thing for momentum and calculate that. And so work I had done with a former graduate student, Shelley Knuth, describes how we calculated all of these exchanges that were taking place. And then just a couple of pictures. So the Aerosonde carried a downward pointing camera so we could take photographs over the plenia. And I just have one or two that I really like. This is, so the scale of this image is about 100 meters across. And what you're seeing is a sea covered by pancake ice. But then the ripples that you see are the waves that had been generated over the open water portion as that momentum was deposited into the ocean. And those waves are propagating out into this field of pancake ice. And the wave height here probably was about 15 meters still. So tremendous waves being generated by these hurricane force winds. Now, as useful of a tool the Aerosonde was, it was very expensive to operate. It was logistically difficult to operate. We had a team of 4 people from the Aerosonde company that flew the plane and maintained it and did the launches, and a couple of scientists there to direct the science mission. And so while the capabilities were impressive with this, the logistics were pretty difficult to manage. And so we started experimenting with flying small, hand-launched drones to make measurements in the boundary layer. And so I'll show you a little bit of the work that we're doing with that, because that's been a very useful avenue for us to do our work as well. And so SUMO is the name of this drone that we're using. It stands for Small Unmanned Meteorological Observer. And we've done 6 campaigns in the Antarctic with this, starting in 2012 and most recently in 2017. And most of them have been near Mcmurdo Station. So Mcmurdo Station is right here. So this is due south of New Zealand. And so we've done some campaigns just out of Mcmurdo. We did one at the Tall Tower weather station that I showed you earlier. And we've done one up in the dry valleys in collaboration with the New Zealand Antarctic program. And then we also took part in a research cruise from April to June of 2017, where we did flights over the sea ice in the Ross Sea. And the SUMO is very different from the Aerosonde. It's a much smaller platform. It's a 0.8 meter wingspan. It weighs a little bit more than half of a kilogram. Its endurance is only 30 minutes. And so we can't do these long distance flights with it. But what we can do is do repeated profiles, in the lowest kilometer or so of the atmosphere, and make measurements of the state of the atmosphere, temperature, humidity, pressure, and wind. And by doing these flights repeated times, every hour or 2 hours over the course of a day, we can see how the boundary layer is evolving in time and really start to understand the processes that are taking place within the boundary layer and its interactions with the underlying surface. And unlike the Aerosonde, where we needed a team of 6 people, 4 pilots and engineers and technicians and 2 scientists, the SUMO field team is just 2 people. It's a remote control pilot and a ground control software pilot. And what that's normally meant is it's me and someone else in my group, whether it's a graduate student or a research scientist. And then, for launch and landing, you need about a 20-meter diameter area that's relatively smooth surface to launch and land these planes. So, you can take a helicopter out to the middle of nowhere in Antarctica or wherever you want to go and set yourself up and do flights and make measurements. And it's a very easy thing to do. I'll show you a video of what a flight looks like with this. So this is out in the dry valleys west of Mcmurdo Station. And so Marwan, he's with the New Zealand Antarctic program. He's going to launch the SUMO. So it's just hand launch. You just throw it, an overhand throw. And then I'm standing next to him with the remote control, and I'll fly the plane for takeoff and landing. But it flies in an autonomous mode during the 30-minute flight. And then the plane's coming in for a landing right here. and that's all there is to it. So a very simple tool to use to give us these measurements of the boundary layer at time resolutions that we normally don't have. So upper air observations usually take place only once every 12 hours from radio sondes. And then we could do these measurements in remote locations like in Wright Valley, which is where we were here, out at the Tall Tower site in the middle of the Ross Ice Shelf. And so it gives us a lot of ability to probe the atmosphere in ways that we couldn't do before. This is a picture of myself and my graduate student Melissa out at our field camp on the Ross Ice Shelf. And you can see, we have a remote control, we have a laptop computer, and that's about all we need in terms of logistics. And then this is what you see on the laptop. It's basically like playing with a flight simulator game. You can see where the aircraft is. You can see information about the measurements. You can see status of the aircraft, how much voltage you have left in the battery, its orientation, all of those things. You can change what it's doing, how it's sampling the atmosphere. So it's a very flexible system. But most of the time, you lay on the ice and stare up at a small little dot, circling hundreds of meters or a kilometer above you, just to make sure that it's doing what it's supposed to be doing and isn't flying off, out into the vast beyond. And so I'll show you a couple of samples of profiles that we took. This was late winter in September of 2016, observations near Mcmurdo Station. And for all of these pictures, the temperature is going to be on the horizontal axis, and then height up to about 600 meters is on the vertical axis. And then the measurements will be from a bunch of different flights that took place over about a 24-hour period. And so this first set of flights, the thing that I want to point out is first, the very strong temperature inversion. Right near the surface, the temperature increases, something like 8 degrees Celsius in the lowest 50 meters of the atmosphere. But the other thing that I want to point out here is how consistent all of these profiles are over a 24-hour period. That's something that you almost never see in the atmosphere, in the boundary layer, that the atmosphere is in this purely steady state, and certainly not in the mid-latitudes where you have the sun coming up and down and a big variation in surface energy budget. So this is a very unique set of boundary layer observations from the polar region. But most of the time what we'd see is that there's a lot of changes that take place in the boundary layer over the span of time that we're looking at. And again, these are all over a span of about 24 hours. So on this set of flights, the main feature was that the surface cooled quite a bit. So this is the boundary layer. It's losing heat to the underlying surface. But at the same time, the free atmosphere above the boundary layer, the part of the atmosphere that's not turbulent, hasn't changed at all. And so from this, we can tell that all of the changes that are taking place are driven by exchange with the underlying surface, because they're all just boundary layer changes. In other cases, what we see is that the temperatures aloft change. In this case, they warmed over this 24-hour period. But then in the boundary layer, which is just this little shallow, 30-meter layer below this inversion, the temperatures are cooling. And so what this is showing us is in these very stable polar boundary layer conditions, there can be very pronounced decoupling between what's happening right at the surface and what's happening aloft. And this is important because most of our in situ observations from the polar regions come from surface observations. And so what's happening at the surface isn't reflective necessarily of what's happening even 100 meters above the surface. And so this is part of why we, put up our tall towers to make measurements, and why we go and do drone campaigns to make measurements to really get this sense of the vertical structure of what's happening in the atmosphere. And then I think one more example. So in this case, we had warming that took place aloft, and the warming at the surface was delayed, but eventually exceeded what happened at the surface. And so again, here we're seeing a reflection of large scale changes in the atmosphere, what's happening aloft, being different than what's happening near the surface. They're both the same sign, but the magnitude is different. And so here there's an interplay between surface exchange as well as large scale advection. And then the next campaign that I'll talk about is one that I was on last year with another one of my graduate students, Gina Joseph. So we took part in the Mosaic campaign. This is a year-long expedition. And here Gina and I are coming back from one of our drone flights. So we're flying a different drone. It's called a Data Hawk, that's built by the aerospace engineers at CU. And Mosaic was this year-long expedition based around the Polar Stern German icebreaker. And you can see the icebreaker was frozen into the sea ice in October of 2019, and it drifted across the Arctic until October of 2020. Gina and I were on the expedition from about here to about here. There was a very fast drift the beginning of the year. And we used the Datahawk drone, and then a team with our project that went after us used a multi-rotor drone as well to make measurements of the Arctic boundary layer from March to August of 2020. During leg 3, when Gina and I were up there, we had real challenging environmental conditions. Temperatures from about minus 40 degrees Celsius up to about 0 degrees Celsius. A lot of storms, frequent winds up around 25 meters per second. That created a lot of active ice dynamics with a lot of leads opening, something that we didn't expect to see, in the March, April timeframe when we were up there. And here you can see the tent that Gina and I operated from and flew our drones, and several leads that had opened between our tent and the ship, which was our home base. And I'll show you a video of what one of these drone launches look like. So this drone is bigger than the Sumo. It's launched with a bungee cord. So that's this orange cord that's stretching out, and we have anchored into the ice with an ice screw. And so Gina's holding the plane on the launch rails. We'll do a countdown, she'll let it go, and then the plane will take off. And this is the first flight that Gina and I did during the Mosaic expedition. So we were real excited to get the plane in the air.
All right.
I am ready whenever you are.
I'll count you down. 3, 2, 1, go. Did you take it?
I did.
Yeah.
And you can hear our spectators were enthusiastic that we got the plane in the air successfully, because we had some technical difficulties with the planes when we first got up at the beginning of March, getting them to operate.
Right.
And so just one picture to show you the types of things that Gina is interested in. So the left picture is showing temperature profile. There's the orange dots, and then wind speed profile are the pink dots. And this is for one of our flights. And then from this, Gina is calculating something called the Richardson number, which tells you about the intensity of turbulence in the atmosphere. And then she's also calculating the magnitude of the vertical temperature gradient as a way to identify the height of the boundary layer. And so what Gina is doing, and we have 89 Datahawk flights from March to August that she's analyzing, but she's looking at characterizing the variability in the depth of the boundary layer. So how deep is that turbulent layer of the atmosphere? How often do features like low-level jets occur? So these are just maxima in the wind speed, right, in the lowest hundreds of meters of the atmosphere. How often do inversions occur? How strong are they? And relating that to the surface conditions, how is this responding to changes in the surface energy budget or the wind speed or things like that? So that's work that Gina's doing as part of her dissertation research. And then the last project that I'll talk about in the next 5 minutes or so is looking at Arctic cyclones. So now we've switched from thinking about the boundary layer to thinking about larger scale weather systems. And this is a project that I'm working on with Liz Cassano, research scientist in my group, as well as Elena Valkonen, a graduate student in my group. And we're using a cyclone tracking algorithm that Mark and his former graduate student, Alex Crawford, developed. And we're identifying all of the cyclone occurrences in the Arctic from multiple reanalyses, as well as a regional Arctic system model that my group has been involved in developing. And I'll just show you 2 samples of what we're doing with this. So the top pictures are showing the number of cyclones per year over 150 kilometer grid boxes in the Arctic. And so the yellows are more frequent and the blues and purples are less frequent. And you can see, the very pronounced North Pacific storm track and the North Atlantic storm track, and that the Central Arctic actually is not terribly stormy. And these are wintertime cyclone counts. And then the bottom is just showing the interannual variability in the number of cyclones within just the Central Arctic for the 3 different reanalyses, ERA interim, ERA 5, and CFSR. And what's interesting is that there's this upward trend in cyclone occurrence in the 2 ECMWF reanalyses, although it's not evident in the CFSR. And this is consistent with what other people have seen, that there's a lot of interannual variability and a bit of noise in the signal looking for trends in cyclone features. But we're seeing some hints of that, and that's work that Elena is doing. And then the other thing I want to show with the cyclones is tying back to the Mosaic expedition. And so what we've done is we took from 1979 to present in the ERA 5 reanalysis, the latest ECMWF reanalysis. And we calculated, how often cyclones were within 1,000 kilometers of the Mosaic drift track that I showed you previously. And we did that month by month. And so the box and whisker plots show the climatology, the 1979 to present. So the center line is the median number of cyclones every 6 hours in each month that would have been within 1,000 kilometers of the Mosaic drift track. And then the boxes show you the 25th and 75th percentile, and the whiskers show you the smallest and largest number over all of those Octobers from 1979 to 2020. And then the star is the cyclone counts for the Mosaic year. And so what you can see is, there are some months where the number of cyclones during the year where the expedition took place were real close to the climatological median value. Other months where it was, well below. When Gina and I were up on the expedition, February, March, out about the 75th percentile in terms of number of cyclones. And then the picture on the right is showing the central pressure of these cyclones, so how deep they were, how strong they were. And the black line is the median from the climatology. The red line is the median for each month during the Mosaic year of the cyclones that were within 1,000 kilometers of the ship. And then the dark gray is the interquartile range, 25th to 75th percentile, and the light gray is the full range of depths of cyclones. And again, what I'll point out is February, March, and April, when Gina and I were up on the expedition, was exceptionally stormy. The central pressure was below the 25th percentile of the 1979 to 2020 climatology. And so we're doing this analysis just to provide a context for what the Mosaic year looks like relative to normal in the Arctic. And there's some months that are close to normal and other months that are very far away from it. A few other large-scale weather type of projects that we're working on. So this is work that Mark Seefeld, another research scientist in my group, is doing. He's analyzing data from the CMIP-6 Global Climate Model Archive. So this is a data archive from all the global modeling centers around the world in support of the IPCC reports. And so Mark has extracted sea level pressure, in this case, from these models, and is analyzing daily sea level pressure over, decadal time periods to see how the models represent the different sea level pressure patterns, the synoptic climatology in the Arctic. And so each one of these little postage stamps, Greenland is right here, North America is on the left, Eurasia is on the right, the North Pole is right in the middle. The blues are low pressure, the reds are high pressure. And you can see the variety of sea level pressure types of patterns that occur in the Arctic, right? So these top left ones are, patterns where low pressure is dominant in the Arctic basin. The bottom right is high pressure dominant. You can see, features like strong North Atlantic and North Pacific storm tracks and all sorts of different patterns. And so it's a real, again, compact way to analyze, hundreds of thousands of sea level pressure observations from this multi-model ensemble over decadal time periods and evaluate what types of patterns each of these models represent. And here Mark has compared the frequency of these patterns to what's seen in reanalysis. And the brown boxes indicate patterns that are simulated less frequently by the model and are seen in the reanalysis, and the green ones are patterns that are simulated more frequently. And so we can do this for each model that's in this ensemble and evaluate how good their ability is to replicate the synoptic climatology in the Arctic. And we can also then look at how the synoptic climatology in the model changes from the end of the 20th century to the end of the 21st century to give a sense of what the weather changes are going to look like as we move through the 21st century. I'll skip this. This is another similar project that Mark is doing, looking at synoptic forcing for oceanic convection in the Greenland in the Nordic seas. And then I'll mention just briefly that my group is also involved in developing regional models. Model that we've been developing for the last decade with DOE funding is the Regional Arctic System Model, and this couples atmosphere, ocean, sea ice, and land at relatively high resolutions and higher resolutions than global models, and allows us to, again, study how the atmosphere interacts with these other parts of the climate system, but in a fully coupled high-resolution modeling framework. And we're using this. One of our projects is, again, a project Mark is working on, looking at decadal predictability of sea ice. And so here we've taken the CESM, the NCAR global climate model, decadal ensemble they've created, the DPLE, and we've used that data to force an ensemble of RASM simulations. And the top is showing in blue the CESM sea ice area from 2000 through 2009, and then the red is the 10 ensemble members forced by RASM. And so you can see, the ensemble members capture a lot of variability, and there's an offset between what RASM and CESM represents. And then the bottom is just the ensemble mean, but overlaid on it, this black dash line are the NSIDC sea ice area observations. And what you can see is that by using this higher resolution model with physics that are tuned for the polar regions, we're actually getting a better representation of the year-to-year variability in sea ice than what you see in a global model like CESM. And so this is another direction that our work is going. And then the last project that I'll talk about is one that Dave Kingsmill, another research scientist in my group, is working on, along with Mark and myself. And here we're looking at weather radar observations from McMurdo Station. This was the AWARE project that Mackenzie's working on. They had installed a bunch of remote sensors at McMurdo Station, including these weather radars. And then the U.S. Antarctic program also installed an operational weather radar for one field season last year or the year before. And so Mark and Dave and I are looking at this data to look at variability in precipitation as well as winds, because these are Doppler radars in the area around McMurdo Station. And there's a lot of topography around McMurdo Station. So Mount Erebus, extends above 3 kilometers right at the doorstep of McMurdo Station. But there are, these other islands, White and Black Island, that create a lot of topography. There are some other ridges and features that are around that create a very rich mesoscale variability in this area. And it's an important area because it's the logistics hub for the U.S. Antarctic program. That's where all the intercontinental flights come into or out of. And so being able to understand, when snow bands are going to come through, or when, strong gap winds are going to be channeled through the gap between Black and White Island and impact the runways is critical for us to know. So this is a project that we're working on as well. So I'll end with just a couple of concluding thoughts. Everything that I'm showing you really is related to how the atmosphere interacts with the other parts of the polar climate system. And we're doing a lot of boundary layer studies using autonomous observations from weather stations and unmanned aircraft. We're using self-organizing maps as a very powerful tool to distill big data sets into meaningful patterns that we can draw physical conclusions from. And we're doing this as well for synoptic and large-scale systems, looking at Arctic cyclones, using these self-organizing maps to look at synoptic climatology and big multi-model data sets. We're developing and applying a coupled high-resolution Arctic model to understand the interaction between the atmosphere and the ocean. And then we're also just starting to move into using surface-based remote sensors, like at this Mcmurdo radar project, to think about what's happening on mesoscale scales in the atmosphere, order of kilometers or tens of kilometers, as well as probing the boundary layer. So I'll end there and open up for any questions. And this picture is a photograph of the Sumo circling over the runway in Antarctica, and the red and white and green lines are just the running lights on the plane as it circles during the time lapse. So I'll end there and take questions.
All right, cool stuff, John. This is great. Very good. So questions, anyone must have some questions here for John. Please put them in the chat or just shout them out, I guess. Mistia.
John, I'm wondering what inspired you to get into the researching atmospheric science and also the cryosphere.
Yep. So I was always interested in weather, sort of as a weather weenie from when I was growing up, so big snowstorms on the East Coast were things that I got excited about. But I hadn't gone into college thinking that I would study atmospheric science. I actually had started my undergraduate degree as an architecture major, and I had to take a general science class for my core requirements. And the one I took was an intro weather class, and I just loved it. And it dawned on me that I could do whatever I wanted. You know, I didn't have to be an architect. And I thought I'd like to study the atmosphere. And so that's how I got into that. And so that was my undergraduate. I got a degree in a geography department at Montana State University with an emphasis on physical geography. And then I went to graduate school to get my master's and PhD in atmospheric science, because that's really where I wanted to focus. And I went to the University of Wisconsin, and one of the professors there, Charles Stearns, had funding for an Antarctic project. And I hadn't gone there really thinking that I would do polar work. I was sort of open to whatever opportunities came along. But Chuck had money to send students to Antarctica, and he asked if I was interested in doing that. And I said, yeah, I'll do that. You know, I'll do it for my master's degree. It's a couple of years of my life. I'll get to go to Antarctica and see something cool that, you know, I wouldn't get to see otherwise, and thought that I would move on and, you know, do mid-latitude weather stuff after that for my PhD. And I just fell in love with working in the Antarctic and the environment. Mark Seefeld actually was a graduate student of Chuck's as well. We went to Antarctica together for our first 2 trips. Yeah, I just fell in love with it and couldn't imagine not doing polar work after having gone there for that first trip in 1994, I guess. And so it changed the entire trajectory of my professional career. It was just dumb luck, as it was.
Yeah, sounds similar to my background. Couple from the chat here. Mary Jo is asking, how often, oops, I'm trying to go back there. How often do you have to adjust the wires, the guy wires at Tall Tower?
It gets visited by the riggers that operate at Mcmurdo. So they're just a group that puts up all of the communication towers and things like that. And they visit the site about every 2 years and tighten the guy wires. Yeah, so it's been up for a decade now, and it's, you know, survived 35, 40 meter per second winds, and it's going strong. So I'm really impressed with that. And it's getting buried, slowly buried. So it's getting more and more of an anchor buried into the ice sheet over time.
Cool. Now I got another. Bruce Vaughn asked, did you encounter any navigational issues related to compass readings while using the multi-rotor in the Mosaic project?
Yes, so Gina and I weren't flying the multi-rotor. It was the group after us, and it was a real concern for us, and we've seen it with the aircraft as well. So the Sumos, when I fly near Mcmurdo, the plane, until it starts flying, thinks it's pointing almost 180 degrees opposite, because the magnetic pole is north of Mcmurdo, not south. So we see that, but for a fixed wing aircraft, it doesn't matter, because as soon as the plane is moving, it knows what way it's pointing. The multi-rotor is much more problematic, and I've seen other groups using multi-rotors in the polar regions that they don't get a good compass signal. The GPS is not giving them a good heading, and the multi-rotors just fly off and, you know, do all sorts of stupid and dangerous things. For us, because we're working with the aerospace engineers at CU for the drones that we took to Mosaic, what they did is they put differential GPS receivers on the 2 arms of the drone and used those to provide a more accurate heading. And so as far as I know, I think they didn't really run into any issues with heading as a result of that, but it was something we were real concerned with. And Gene and I saw some flaky things with GPS with the Data Hawk as well. But again, once the plane starts flying, it knows what direction it's pointing, and so the autopilot is able to deal with that. But it is something you have to be careful with.
Another question. Does RASM, R-A-S-M, include water isotopes in the modeling?
It does not. Yep, that would be a nice next step, but we don't have that expertise within our group.
All right. Then another one. Were any UAV observations made over melt-ponded ice during Mosaic?
Yes, a lot during leg 4, the leg after Gina and I were up there. So that was a main focus for the multi-rotor, was hovering over different ice types as the sea ice was melting and making radiation measurements. But we also flew the Data Hawk over those surfaces, as well as over the leads that started opening when Gina and I were up there. So we were sampling a lot of those varying sea ice conditions with both the fixed wing and the multi-rotor.
Cool. There's a lot of interest at NSIDC about melt ponds. So,
Yes.
well, we're just about to running out of time, and I'm sure that John will be open to more questions if anyone can bring them to him, an email or whatever. Okay, but this is fascinating, and it's great to have John and his whole crew and all his grad students at NSIDC, and they're together with my grad students. So we have this huge critical mass now, and this is just a wonderful thing. So with that, I thank everyone, and John especially, for this great talk. And
Well, thanks,
we'll talk
everyone.
to you later. Yeah. Bye-bye.